Așa, bună ziua, stimată audiență. Eu mă numesc Olga Michalciuc, vă prezint lucrarea metodei de determinare a proteinelor carbonilice și derivatelor lor și importanța patogenetică. A fost făcută lucrarea de Valentin Cudumac, Lilia Andronache, Valerian Arpantea, Olga Tagariu, în laboratorul de biochimie, în Centrul Medicină Moleculară și Medicină Personalizată. Și a fost o conlucrare foarte frumoasă cu Institutul Mamei și Copilului, cu Jana Bernic și Elena Tarca. Acolo am lucrat cu laboratoarele de chirurgie infecțioasă pentru copii, departamentul chirurgie pediatrică, ortopedie și anesteziologie Natalia Gheorghiu și conlucrare a fost și cu Centrul Științific-Practic Național de Chirurgie Pediatrică în Spitalul Mamei și Copilului. Așa, speciile reactive ale oxigenului reprezintă esențiali mediatori într-o gamă largă de procese atât fiziologice cât și patologice, ele incluzând atât îmbătrânirea cât și dezvoltarea bolilor cronice. Speciile reactive de oxigen sunt implicate, se formează atât în condiții fiziologice cât și în condiții patologice. Implicarea fiziologică induce reglarea expresiei genice, controlul răspunsului imunohumoral și celular. Sunt importante în calitate de molecule de semnalizare și de comunicare intra- și extracelulare și, în ultimul rând, în menținerea homeostazii. Speciile reactive a oxigenului se formează continuu în metabolismul normal, iar nivelul lor excesiv induce un dezechilibru în lucrarea dată în axa special la oxidarea proteinelor și aminoacizilor, care induc o gamă largă de produse intermediare și, în special, ceea ce am studiat, proteinele carbonilice. Rolul speciilor reactive oxigenului a determinat, adică rolul lor dual, determină nevoia crescută de a efectua metode sensibile, reproductibile și rentabile pentru monitorizarea stresului oxidativ. De aceea s-a lucrat pentru optimizarea metodei spectrofotometrice pentru cuantificarea proteinelor carbonilice, care sunt la moment recunoscute ca marcări ai deteriorării oxidative a proteinelor. Și am studiat metodele existente în literatură. Cea mai utilizată metodă este derivatizarea grupării carbonil cu 2,4-nitrofenilhidrazină, ducând la formarea de nitrofenil. Ceea ce se efectuează la moment are un șir de dezavantaje, sunt metode laborioase, consumatoare de timp, necesită cantitate mare de proteină. De asemenea, metoda conține multiple spălări ale probei și împreună cu etapele de precipitare și resuspendare duc la pierderi până la 15%. 2,4-DPNH în sine, precum și o serie de compuși biologici, cum ar fi hemoglobina, mioglobina, etc., pot interfera cu proteinele carbonilice, afectând negativ precizia și acuratețea metodei, constituind potențial surse de erori. Toate acestea am vrut să le nivelăm, da? În care parte sunt? Acolo. De ce scopul studiului nostru, lucrării, a fost elaborarea metodei optimizate de determinare a proteinelor carbonilice în ser și sau plasma sanguină, ce ne-ar permite creșterea productivității, reducerea timpului de execuții și a costurilor prin reactive și, nu în ultimul rând, să poată fi aplicat în orice laborator modern de biochimie medicală. Apăsați. La mine nu scrie. Detaliile tehnice a metodei au fost descrise amănunțit în lucrare. S-a efectuat în microplăci fotometrice. Toate probele numai decât trebuie să fie făcute în duplicat și în final grupele carbonilice se calculează pe baza coeficientului de extinție imunar și se expresează în nanomol miligram proteină. De ce nu merge? Este timp să vedem metoda mai mult. Da? Nu merge. Vedeți cu, apăsați cu... Da. Și metoda aceasta optimizată așa, a fost testată cu colegii noștri care au vorbit la Centrul Mamei și Copilului și laboratoarele științifice de acolo, de copii cu vârsta cuprinsă între 0 și 18 ani, cu anomalii congenitale ale rinichilor și tractului urinar. Probele biologice s-au colectat intraoperator și postoperator. S-au făcut câteva grupe, una cu copii cu hidronefroză, 2 cu reflux fizico-ulceral, 3 cu megaureterohidronefroză și grupul control. Așa, rezultatele investigației s-au testat proteinele carbonilice și derivatele acestora, așa, AG și de aldehida malonică. S-a observat că rezultatele indică o creștere semnificativă statistic a nivelurilor proteinelor carbonilice și derivatelor în toate subgrupurile de pacienți. Aceasta ne indică o deteriorare foarte considerabilă, unde formarea speciilor reactive de oxigen depășește capacitatea antioxidantă totală în spațiul extracelular la acest copii. Deci putem menționa că carbonilarea este una dintre cele mai remarcabile expresii ale deteriorării oxidative a proteinelor. Și metoda la care am atras atenția permite evaluarea acestor proteine preformate prin diverse căi și mecanisme. Aceste mecanisme includ oxidarea mediată de speciile reactive de oxigen, glicoxilarea carbonhidraților cu formarea produselor finale de glicare avansată și lipoxidarea produselor cu formarea de aldehide malonice. Deci, utilizarea proteinelor carbonilice, determinarea lor și derivaților lor ca biomarcheri ai stresului oxidativ are mai multe avantaje în comparație cu măsurarea altor produse de oxidare, datorită formării lor relativ timpurii, a stabilității lor, ceea ce am confirmat prin cuantificarea lor în malformațiile și bolile renale la copii. Această lucrare este de importanță majoră, deoarece mecanismele leziunilor renale, nefropatia obstructivă congenitală și fiziopatologia moleculară a fibrozei interstițiale renale sunt în prezent discutate pe larg în literatură de specialitate, cu scopul de a identifica noi biomarcheri și ținte pentru îmbunătățirea rezultatelor tratamentului. Așa. Și în concluzie, dezvoltarea tehnicilor noi, rentabile, extrem de sensibile și precise pentru evaluarea proteinelor carbonice, care pot fi utilizate pe scară largă în practica zilnică, este de mare importanță. Metoda NPH optimizată în laboratorul nostru poate fi utilizată pentru diagnostic, evaluarea eficacității tratamentelor aplicate și monitorizarea afecțiunilor patologice manifestate cu exacerbarea stresului oxidativ. La moment, metoda este implicată și la Centrul Medici Copilul și în laboratoare de chirurgie, de infecție chirurgicală și în departamentul diagnostic de laborator. Adică metoda este inovatoare și de acum se implică. În principiu, atât. Da, vă mulțumesc pentru atenție.
Mulțumesc de noastră.
Thank you very much.
Лаборатория дупалиста есть Rodica, Siminiuc și Dina Turcan. Sunt prezenți? Sau следующий Șerban Михайло и Александр Андросов.
I'm Michael Șerban, professor from National Technical University, Kharkiv Polytechnic Institute, Ukraine, Kharkiv. And I want to present our work that takes wireless multi-sensor platform for long-term human gait analysis. The relevance of this work is driven by the growing number.
There is a small button. Go back, Michael.
Okay.
Small button. Goes back.
Sorry.
One more.
Yeah. So it's huge growth numbers of people, person with amputation. According to the World Health Association, 445 million individuals with traumatic amputation globally, and unfortunately we don't have any official statistics in Ukraine, but for example, Wall Street Journal estimated the number of Ukrainian soldiers is into prosthetics between 20,000 and 50,000. And for now, or 56,000 Ukrainians receive in several last years. 2008, 208,000 rehabilitation procedures, so it's a huge number. So we need effective object tools for gait assessment, not only in laboratory but also under real life and everyday conditions, implanted in limb prosthesis and checking the asymmetrical walking, checking the problems with limb biodynamics and etc. Known solutions for this area. So gold standards is mock-up technology. So you can see here Vicon MX motion capture system and makers of Detract. So it's very good, cool, very very good methods, but these methods only laboratory using. These methods only only under assistance with laboratory personnel, and moreover, this methods is very expensive. Not for real life using. Another way, this IMU-based technology, we can see the known technology that used IMU and use gyroscope, accelerometers, and magnetometers for measuring some parameters of walking, some parameters of gait. But these researches is one problem. When in this researches, scientists use several devices. These devices not synchronized. Only each device connect with local time, and synchronization is not good. This lead to summarizing errors and summarizing errors and collect phase distortion. What we proposed. We proposed solution when we have from 4 to 8 sensor devices, and we use one mesh, one synchronized time for synchronization of this device. You can see our device on this slide. Pointer. Oh, sorry. We can see our device that we use on this platform. Connect through the BLE core to the smartphone, and smartphone processing like a hub that collect our data, all data. Each sensor have a time slot and internal time that collect to the one frame 80 milliseconds. It's 8 samples in 10 milliseconds each. And then we resample this raw data and interpolate this data to another mesh, to another time sequence in real in real time. So for the after that we use interpolation and this interpolation data have RMSE like on this slide, no bigger than 007 G or 6 of 12 degrees per second. So it could be good. It can be good for no less than laboratory researches. So Here you can see our sensors with on the left. When we testing these sensors, we use three formats of this experiments. It's a normal walk, then limping on right leg and limping on left leg, and then we check the changes with these formats. Here I tell about this method deeply. On the next day I have do another speech about methods of calculation, angles, and asymmetrically, and much more. But here I just present hardware and software processing for like preparing for like tool for method. Okay, so this an example when we have 4 sensors, left, right hip, and left, right shin, like this, in one grid and one timestamp, and this curves that showed the left chain angles and left hip, right hip angles for founding real asymmetrical, real parameters that give us possibility to check normal of pathology walking. So in conclusion, I want to say that this platform give us possibility obtain stronger synchronized data from IMU sensors, IMU minimal 4 sensors, maximal 8 sensors. We can see connect to our hub to smartphone, and as you see, it's not bad results for this hardware software platform, and this platform, as my opinion, is not bad tools for our research. Thank you for attention.
May I ask a question? What's the cost of the system for sensors plus what else? Maybe some consumables.
This is just
Let's say several hundred dollars.
just experimental tools. Like MVP, right? So it's maybe $40 per sensor,
So
including printing box, belts, not include walking.
so less than $200 in total if you use 4 sensors.
$200 in total. Maybe yes.
So compared to let's say other systems, it's quite cheap.
Chinese tools give price like $10, but Chinese devices, unfortunately, we previously use WIT sensors.
Wait.
WIT sensors. That's like same IMU sensor, but we can't obtain raw data. We have to use only pre-installed software and just look like a toy. Not seriously. We can measure any parameters, and we can't trust this device. So we design our device because we trust ourselves, myself. Yeah.
Yeah, if I may, just a little bit addition to your question. The key comment here, because I'm just also like the man of the total group who has make this study, not particular these devices, but the problem is that cheap and known wearable electronic solutions use Bluetooth adapter, and they have a lot of noise and missing data during the measurements. And we stuck with a problem of synchronization between the 4 different devices in the same time, especially because of the problem of this data processing during the receiving. For example, then just someone walking in the treadmill with these 4 sensors, and some new man just move through the mobile phone, they switch on Bluetooth, and the data was missed. Yeah, and all the data was missed. So that's absolutely not usable. This sense. That's the first one. And the second is very important here, that then you try to install the devices into the human legs. That's also a huge problem, because you need to be absolutely sure that they are fixed enough, and they're not moved, they're not sliding, they're not moving, and that provide for us an idea to make patient-specific 3D printing technology. So we just print special elements that just install into the legs, particular to the legs of patients. That's a small additional cost, not only for sensors, but also you need to print and some time to make some scanners, some measurements of the legs, to be absolutely sure that the devices are installed completely properly in the correct places and do not move during the walking.
Thank you, Oleksii. Moreover, it's just first step for designing this sensor, this platform, and this platform is the base of universal platforms that installed in Lulin protheses. So we want to extend original protheses, like a smart prothesis that give not only us this data, but we construct biofeedback with patient, and we construct biofeedback with customer, and customer can check own walking, own parameters of walking during walking. So that's all.
Thank you very much.
Thank you.
That was Mikhail Shishkin and Alexander Androsov.
Yep.
The next work is biomechanical analysis of bone implant interaction in a femoral prosthetic reconstruction. The author is Denis Levitsky, and Oleksii Larin, Alexander Sitenko, Roman Tomashevsky, and Konstantin Bartin.
No, Denis Levitsky, exactly. Okay,
Change the presentation.
Change the presentation. Hello, everybody. First of all, many thanks to organizers of the conference to be a possibility to be here today in Chișinău and to make the possibility to listen to colleagues and to spread and to share our ideas. We are originally from Kharkiv, from Ukraine. I'm presenting here at National Technical University, Kharkiv Polytechnic Institute. You could see that on the slide on the left side. And I'm just one of the member of a huge group of of researchers, 2 professors and 2 PhD students who are engaged in this study very motivated by the current situation, the problem for us. Before I will continue to go deeply in the details of the presentation, I would like to say that particularly this research was done in cooperation with Medical Institute, that is in the Harvard Institute of Spine and Joint Pathology of National Academy of Medical Sciences. Right. So we are cooperating with this medical organization, we are technical university and they are medical guys to help the patients with amputations. Actually, that is the content of the presentation. It will be not quite a big one. And the picture also was shown by Michael on the beginning. That's a graph that shows how many cases per year we have about the amputations in the worldwide. So in the world, we have as much as 445 million people who have traumatic amputations at the moment. And in Ukraine, unofficially, we know that at least 100,000 people are suffering from the problem of amputations due to wartime since the last 2.5 years only. And the situation will be dramatically rising next years, absolutely, even if the war stopped today. So that's why we look more deeply in how we could help these people. The main problem actually here that is quite young people who are suffering with the problem of amputation. So they are willing to be inactive in their physical life, and the prosthesis should be as good as do not really restrict their normal behavior. So what we have today in the world, there's a lot of different commercial and scientific research within that, and we have a lot of different prostheses, and even in Ukraine at the moment we have like a huge number of different humanitarian companies who provide this different type of prostheses. But what about the typical prosthesis? You could see here in these pictures, borrowing from the internet. Here are these specific devices. I mean, this one, this one. That is a special tool that is like in a veer onto some part of the leg that exists. Yeah? And then the patient try to rehabilitate to this and try to study how to walk, to run, or whatever. And the problem is that this particular common device have additional flexibility in the connection between the rest part of the leg and the prosthesis it is. So they have additional flexibility, and everybody's have to tune how they will actually move to study the muscles movement on the legs and to reload and to overload additional the legs. So another interesting aspects that today's medical professionals provided is implant integrated prosthesis. That's a little different story. That is this picture. If some specific implant is installed into the bone directly, and then the prostheses are integrated with this implant altogether. With this, we improve the processal controllability, because this will be also a bionic functionality actually in these legs in this case. The second one that is could be probably reduces this process of additional flexibility between the prosthesis and the leg. So that is a very interesting aspect. And also very important here moment that if the amputation is very high of the leg, there is no additional part of the rest of the leg, then we could install this traditional prosthesis. So in this case, we just limited only this solution to put the implants. So with these implants, we need not only just a medical problem, but also a mechanical and engineering problem, because we need to create these devices, these implants, and the prosthesis as a total mechanical system, and also to look in additional what will be between the stresses and deformations in the bone, in the rest of the bone, because this additional metal part could make some additional destruction actually, especially for, as I mentioned, for young patients who try to be physically active, go to the gym, go to the work, to the office, whatever, and they just start jumping or running, and that will be created extremely additional load to the rest of the part of the bone with these metal implants, and that could actually create a problem with strength and durability for both, for implant and for the leg. And also a huge question about the optimal design parameter of this. So we was motivated to that and trying to look at that from a mechanical perspective, being the representative of a technical university. And what we're interested here, we're interested in, that is also a very important point on this slide. If we try to implant the prosthesis, then it takes some time, quite long, months, while the osseointegration process will happen. Then the bone and this implant will be integrated together. That takes like some months, this process. And during this time, the muscles of patients and psychological state of the patients are stressed very much. And for this reason, the rehabilitation specialists motivated everybody to use these implants and these prostheses as quickly as possible. But that's the question, how to use them. There is some program, there is some specific exercises or gym exercises to this very early stage usage of some implant stage. And for answering that, we need to study that in details. I mean, not only the interaction between bone and implant, but also the different type of this connection between them. So that is what we are interested in. Our idea here is to look at that from a mechanical perspective. So the main objective is to study from the computational perspective how the osseointegration, the degree of osseointegration will influence on mechanics of prosthesis, implant, and bone. So for that reasons, we created a finite element modeling of the system femur implant prosthesis. So that is a picture of a real implant that was designed and manufactured by our colleagues from the Institute of Sitenka. And that is an oxide of titanium, that's some other carbon-to-carbon composite material and some other metal parts. And they provide for us of this real objects, and we build the mathematical model. And also we build this FEM model together with the human bone. Yeah? And we installed it artificially, surely, to the bone in 3D modeling. And also we create additional part of this one, a little bit schematic, that as additional installed this prosthesis, because the real boundary conditions, I mean the conditions how the forces and displacements will be transferred from the real loading to the implant into the bone as crucial here. So that's why we was motivated to build this part as well. A little bit schematized. It's not it's in the real, because we're not interested in this metal part, interested only in what happened with the bone. And that's some parameters of this system, some material properties borrowed from literature. And after that, some different schema. You could see, for example, on this picture, that the FEM mesh here is quite rough, but in the bone it's quite fine. And so we make also a very interesting study. How to model the interaction between the part of the prosthesis and the bone. We think that it's like in a contact condition, so-called dry friction contact. And in a very early stage, then it's just installed, they have a friction like bone to titanium metal part. But after osseointegration happens and then it's finished, the probability will be like in a bonded connection, when the two materials are completely stick together. So that's a two extremely asymptotic part. And everything that between us, we spread it on some range and do a study by varying the parameter of the friction between this from very small up to the almost infinite. And what we and what we actually received here. That's some math about the criteria of the strength. It's more parameter. So that is in a bone, and that is in the stress concentration. That is like a part of the bone that happens here, and that is a concentration what we could receive. And that's a deformation. If somebody will be interested, that is in the paper also presented, and we could discuss in many details. But what is important that actually this osseointegration type influence significantly. So the stresses inside of the bone could be very small in some intermediate state of this osseointegration process. But while this osseointegration happens, the stresses actually could be rising, and on initial stage it also could be quite bigger. And also this is important that the picture, the pattern of the stress is also different. So if osseointegration is only in the early stage, then the stress concentration are on a very actually here on the end of the carotid bone, and when we go into complete osseointegration, the stress concentration will happen here. Then the implant is finished, actually, at the end of the implant. So it's switch on, the concentration is switch on. And actually that's interesting results for medical rehabilitation professionals who are interested in this program of physical activity, what should be restricted in movement and what could be allowed to patients in different stage of osseointegration process. That's the different picture about that. So, in conclusion to this presentation, we try to provide from medical professionals some mechanical aspects of what happens in this very important for us, and I think globally, the problem. They make numerical simulations. At the moment, we're interested in patient-specific system because we have actually the 3D scanners. We actually at the moment have different typical pictures of OCT, and they could build these bones patient-specific, and they could create the simulation in real time for real patients to provide them and to medical professionals, not like associative, intuitive knowledge of what should be happens with different design parameters, but reasonable, scientific or reasonable aspects. And also we, at the moment, are interested in very many perspectives of how this study could be going out. The first one, at this moment, we only study a situation that the human just stayed straight on its prosthesis. And in this case, we actually obtain a very reliable results that nothing happens to the bone. Yes, stress will be bigger or smaller, but actually it's not broken. Everything will be okay. And that's not surprising because that's like everything in practice happens. But what if the person will jumps or runs and then it will be dynamic loading? Reality said that the cracks happens, so we're interested in studying this. Another very interesting performance that about this osseointegration degradation over the time. Actually, once successfully operation finished and everything is okay and the patient is rehabilitated, it going to the real life, 10, 15, 20 years, and no one knows what will happen later. But that's absolutely true that the bone, as any material, have aging process, have fatigue process inside, and this degradation will definitely change everything. And we're interested in trying to look at that, to study that before some awful things happens. And the last one, also they're interested about the comparative analysis of different implant designs. There is like at least 5 known from my side, different designs, how the implants could be installed into the leg. And which one is better to choose is also a very open questions. And from a mechanical perspective, we are at the moment trying to examine these different configurations. And actually in Harvard will be a very nice conference about that. There we try to present these comparative studies for several type of designs. Well, thanks very much. And one more time, thank you for getting me this conference. Thanks a lot.
Thank you very much. Maybe some questions?
Show please the plot.
This one?
Yeah. Which conclusions can a rehabilitation professional make from this?
For this part, yeah, then they have a very low level of the sliding friction between the implants and the bone, and we have that's not a correct picture because for this point, for minimum point, for this point, we have in different place of stress concentration. It's on the edge of the bone. So the rehabilitation specialists understanding that the concentration of the stresses in this state, not in the place of it's changed. So the program of rehabilitation should be adapted according to that. I mean, because the stress is migrated from one place of the bone to another, some type of exercise, physical exercises, should be modified. That's the main results from particularly this study, because that's just a static, straight up stating, and actually that's nothing absolutely fantastic from medical purposes at this moment. And that's just a first preliminary results to try to model this dynamic behavior. Probably in the dynamic, because it could happen to this migration, it could be more interesting for medical practitioners.
Of course, you may have here some wave processes in the bones and so on.
Yeah.
And do you have any experimental confirmation of this data?
No. We only what we have at the moment from medical practice. They are installed these implants already in some bones of they say that biomaterials, and that's actually not human beings. And for some human beings, there is an example that the bone is cracked during the jumping or some other dynamic exercise. Because after the successful rehabilitation, these persons, young guys, move to some, for example, for gym. I have one friend of mine who in the gym with such a prosthesis, and I always told him that be very careful to not really load your leg. It's not like something that you really need to do. But they would like to feel the real life, to be full of emotions. And that's actually what really happens. It's like cracked additionally, and then additional surgery, additional cutting, the smaller legs, this rest will be, and that's a huge problem actually. Yeah, that's what is like more motivation, not experimental evidence of our research actually.
Did you manage to estimate the error of your computational simulation?
Yeah, sure, absolutely. For this particular results, we estimate typically the different mesh size of finite elements. I mean, it's that this is an FEM, yeah, it's finite element modeling, and so we have here a finite elements, a very small piece of virtual space that is approximated by the so-called shape functions, yeah, and dependent on how dense of this mesh, the results of integration of total equations of elasticity will be changed. So that's a very initial check of the error. Then you make a computation. We make these computations, the different mesh density, and for that we have a 5% error, and they think that is okay because the result, the material data is not like as good as 5% actually. So that's why we say that it's okay. But your question is very nice, because actually the error should be estimated not only from the integration point of view, not only from pure math, but also from the physical modeling and also from the adequate of this additional part that the model to correctly transfer the loads. Yeah? And for this case,
like an ideal case to which you could compare and estimate your error.
Yeah.
Then you don't have this ideal case.
Yeah. But that's like an idealistic future. We try to figure out. Professor Haluza idea that we need an experimental evidence of something like this, even in the modeling style, will be definitely help with that. And probably we will do that with our colleagues from university or from institute.
And just another question: is the coefficient of friction enough for this? I mean, for all this process of osseointegration?
Yeah, but actually,
don't you need to have a lot of other mechanical, let's say, coefficients that you should take into account? Or what do you take into account?
We take into account we have this all these mechanical parameters of the materials. Yeah, this one. Yeah. All these parameters of the material, and this friction coefficients was only one parameter that is varied. I mean, we try to use it different from one position to another to model the osseointegration process. And probably that's also not a good model, because this osseointegration probably has some specific layer, or then the bone is integrated actually with oxide of titanium, and in reality we could model this layer and try, and that's something that we will make in the very next future. Yes, that's right. Not only by the friction coefficients, but also the specific layer that will represent this. Yeah.
Good luck on that.
Thanks very much.
And what is this interface layer between titanium and the
You mean about thickness?
Yeah, what is it?
Up to 10 or 20 micrometers.
And its structure.
I don't know. We need to look at the microscopes. Actually, that's something that oxide titanium just somehow integrated with the bones. That's just rising around that. I'm not sure.
So it like works as a matrix for the bone tissue, sort of.
As far as I understand this correctly, yes. Yes, it's like in a box and then it's like also integrated. But because we have two different implants, one inner, this one is inner, that is just installed in, but there is in some outer. But osseointegration happens either there, either in these places, and probably a little bit different. There is also soft tissue, like in the skin and fat and muscles that are rising here as well. They are growing during the process of treatment. That also will be influenced somewhere.
Okay, yeah, I see.
That's a lot of questions because there is also a blood flow somewhere, and if there is like a problem with that, then some part of the bone will be like a die, and in this case, the osseointegration also will stop. And the medical guy said that will be also a problem. What they figure out in reality, then try to create some specific treatment for that to help the bone. I don't know how to say to have some sources for osseointegration rising process. But we cannot model at the moment. That's absolutely.
So this drilling process, it removes the bone marrow, right? The core of the bone. This probably affects the bone health.
Sure. They drill the hole slightly, and then they just hammer this part inside. It's like
so
not the funny procedure.
Long term, who knows what is going to happen?
At this moment in the world, we have 5,000 patients that are successfully have this treatment.
5,000
Yeah, totally.
So it's
not too much.
Number compared to normal usual prosthesis.
Yeah, absolutely. Because for usual prosthesis they have 1,000 and 100,000, but for this only 5,000. I mean for the legs. But we have such implants installed in a tooth. And there's a lot of such prostheses in this how to face tooth surgery.
Yeah, so drilled inside.
Yeah. But it's smaller, and the loads
does not replace the bone marrow.
Exactly.
Thank you very much. Maybe some questions?
Okay, thank you.
Was Mr. Denis Lalinsky. So the next.
No, I'm actually lying.
Sorry. So the next work is the protocol developing for visual function, testing efficiency, and increasing for regular and professional drivers. And the speaker will be Mr. Barbara Brown. Is here? No. The next work is design and realization of a UVSC and ozone-based device for room disinfection. The speaker is Ionel Șerban. Is here? No. Next work is multi-scale, multi-module correlative characterization with micrometer accuracy for material science. The speaker is Oleksii, Charlotte Niger, Rafaela de Bastian, Torsten Schirer, Matthias Mehl, Divang, Christian Kubel from Germany, Institute of Nanotechnologies, and the Karlsruhe Institute for Technology is here. No. The next one is mechanical ventilator prototype for self-disinfection and ozone therapy function for room disinfection. Corneliu Nicolae Druga is the speaker. Is here. The next work is brain-computer interface enable decision support for human behavior monitoring in safety critical context. The authors are Oana Izabela Stirbu, Ioana Raluca Adochia, Șerban Teodor Nicolescu, Cosmin, Carl Banica, Gheorghe Călin Sirițan, and Felix Constantin Adochia is here. The next work is assessment of the effects of spectral non-stationary of sound signals of biosystems. The authors are Evgen Sokol, Pavlo Sharkov,
Здесь. Здесь.
Константин Колесник, Татьяна Германическая и
One
Юрий Санин.
Так это же после...
Вы же уже ускорились.
Они же не
We
знали,
are on the
что...
second page because we already finished
They do not,
But they did not really know about that.
yeah, because they do not
Yeah,
know.
They probably did
I'm
not
also
section.
interested because Mr. Sokol, yeah?
No,
No. Okay.
because he doesn't know that we sped
We're
up.
waiting for
Because
6
he's-
p.m.
he's,
Oh,
speaking.
4 p.m.
Yes, we should wait, of course.
But Pavlo Shapov is here, but probably in another section, listening to other presentations.
Mr. Shapov is here, yeah?
Yes.
In the room
another-
5.
But in the room 5 at the
The
moment.
room 5 for the Nano presentation, yeah?
Yeah.
Okay, so yeah. After 4 o'clock we should return
So,
here.
so now we have a
Yeah, sure.
Yeah, from 3:30, 3:30 and 4. Because we already have finished the presentation.
The first our presentation is Oleksii Vugnov, multi-scale, multimodal, correlative, and so on. No, yeah. The second presentation, mechanical ventilator prototype with self. No. The third one, brain computer.
Oh. Clicker?
Here
There.
Hello, my name is Felix Andochi and I will present you brain-computer interface, embedded decision support for human behavior monitoring in safety critical context. In this paper is presented some part of result from an European founding project. The main idea of the project was to build a robust machine to detect dissimulated behavior for people who works in critical infrastructure. The project is divided in two sub-models. I will present it only one model here. First model is in indoor detection with controlled environment, and the other module is outdoor in real situation. For indoor situation, we acquisition EEG for 32 channel. Some peripheral physiological signals like galvanic skin response, heart rate variability, pulse, pressure, skin temperature, and blood pressure. Here we see some presentation and the device connected to one of my colleagues. After we acquire all the parameters, we extract some feature from these signals, such like EEG frequency band theta, delta, alpha. We use some filtration for artifacts, and we synchronize all the signals to have the same timestamp. We also monitoring phase for micro expressions in visible spectrum and infrared spectrum. And also we study also the eye tracking to see or the dilatation response of the eyes. The problem was for the study, after we acquired some signal, we receive a different response from the same subject, and we try to manage this problem by study also the I don't have plus a point to see the environment is the same. For example, if it's hot outside, it's a state of the subject have a emotional state. If it's raining like this, it's different response of emotional state. For another situation, for example, I see if we have some CO2 in the room, we have a response, and if it's different, we have more rapid response. And we studied also to see to have the same environment, and we controlled that environment using air filters, air conditioner, and to have the oxygen level the same in the room. This is the architecture of our indoor system. Here we see all the components from the patient. We acquired with GTEC. We use EEG for 32 channel, and also we use FNIR to see the brain saturation of oxygen. It's like remedy functional remedy in real time. It's like the same, but not the same cost. Air module and all the physiological signals. And also we have some sensor to see if the patient, the subject is moving on the chair. And also we have an accelerometer. All of this data are synchronized with one camera, 4K camera, and one thermal camera. And also we have an eye tracking detector. All the data are encrypted and send it to a database storage. And here we have three servers. One is for storage, one is for application, and one server is for processing all the data. We have streaming video and also streaming from subject vital signals. Our application results are in condition if the subject is have stress, burnout, anxiety, and also we use protocol to see if he has dissimulated comportment by asking some question, and for that question we receive a true or false state, like we see here. And this is the score of trusting the results. The accuracy of our IE is 22%. We use in the study, and for training the IE we use students, and they lie a lot. And because of that, some parameters are not so high. This is the main problem for this project. And our machine learning. We have two machine learning, one for cognitive emotion and one for telling if he's lying or telling the truth. Both of this AI module can be improved by adding more data to AI. This is the project was founded POC project. Thank you.
The questions, please. Mikhail.
Yeah, I have a question. This system seems quite similar to a traditional polygraph, right?
Yes.
At least in its idea. But
Yes. We use also the polygraph.
Mhm.
The problem with polygraph is they have more problem. The polygraph is not for detecting lying. The polygraph is inducing stress to recognize if you lie.
Mhm.
The problem with polygraph, if you have different stimuli, you can lie.
Mhm.
For example, if you have a small nail, and you put it on your seat, and if you telling truth, you press it and it responds. You say you have the same response from your body.
Mhm.
And if you telling lie and press again,
Mhm.
it's the same response because the nail provoke
More powerful impact.
yes.
Yeah?
Yes.
Uh-huh.
And another problem with polygraph, if you take 2 pills of beta blockers,
Mhm.
everything is
Mhm.
done. And another problem also with our system, if you don't have a scope for questions, the response is very low. For example, if I ask you, did you eat today? And you say yes or no, is the same.
Mhm.
Also for polygraph, also for our system, but for EEG, for example, you can lie, not lie with your brain. You can lie with your heart, but with your brain no. If you train, for example, if you meditate to control your heart,
Mhm.
for example, special troops, they meditate to keep polygraphic
Mhm.
test.
And this system, it measures more parameters than the polygraph.
Yes.
For example, polygraph does not measure facial expression and
Yes,
so on.
and also the EEG brain work.
Also another question. You mentioned this system is designed for people in critical applications. This is, for example, like...
Yes, for example, firemen. If they do the training and they go to simulating fire extinction, they know in their brain they have some areas where they are safe. And because of that, the brain is lying to them, they can be firemen, for example. And in real situation, they comport different because it's more stressful and have different waveforms.
So you can use this system to monitor people in real life situations?
Yes, this is the PA1 for this PA1 is for indoor, and the other one is for outdoor. We use more cameras to see it, and it's more based on how body is moving in the real situation.
Thank you.
Welcome.
So if I got your point right, you told about online recognition, right?
What?
Oh no,
Online
recognition. Online. So online.
Yes.
It's not in lab.
No, because we have to process all the data and to see after that.
And
For example, real time it's online.
real time, you make a decision in real time.
Yes, but we have
But not online.
So
30 seconds delay for real time.
this is gonna be my question. What delay?
30 for real
minutes.
time it's 30 seconds.
30 seconds. Oh,
Yes,
not big.
yes.
Good. Thank you.
Yeah. So your accuracy of your model 72%. Yeah?
Yes,
That's for true or false question.
yes.
What about the recall?
The record.
Yeah, I mean, then you try to estimate the error of AI prognosis.
Yes,
You could check the accuracy. That's the total correct and not correct answer. But also you have a mistake number 2. Then you make like a right decision, but actually it was a mistake. For example, there's a matrix: true, false, false, true, false, false answers.
yes.
And so we could introduce several matrices for the estimation of general error. You show only accuracy, but what about all others?
We don't study it,
Yeah.
but we
Okay.
take in.
Because that's also interesting about
Yes.
there's always a mistake of the first type and the second one, always,
Yes,
in any prediction. And the question is, what about the sensitivity?
yes. I said the main problem was I didn't have some subject to train the AI correctly.
Mhm.
Because, for example, one student of mine told me on the paper he names Messi. And because of that, my parameter, or some of the parameters are.
Why do you think that the students is not a good subject? They are subject as any other human being, actually.
Yes, maybe if I ask him, did you cheat on the exam? And yes,
Students are humans as well.
yes.
Any other questions? No. Thank you. Our next presentation, assessment of the effect of spectral non-stationary of sound signals of biosystems. Pavlo Shapov, just
I'd like to present my report on two language, Russian, English, and French. French pour vous, oui. Vous comprenez le français, c'est pour vous. Bien. Pourquoi en Russian? I have a level of knowledge of English level, English language, and between A1 and A0. French, I speak and I understand fluent. Yeah. Russian.
Native.
Это. Yeah. Firstly, on Russian. Откуда возникла задача? Потом переведу. Я работаю с госпиталем военным. Я предложил 2 года назад восстанавливать гормональные показатели при обследовании раненых с помощью методов прогнозирования по большим базам данных. Обучается система на большой базе данных, а потом она восстанавливает то, чего нет. Почему гормональные показатели? Они несут информацию о тяжести ранения больше всего. Вот. Более того, эти гормональные показатели, как показали исследования, можно использовать для прогнозирования операционных кодов. Когда сложные операции многомодальные, то оказывается погрешность 10-15% может быть. То есть молодые врачи могут пользоваться прогнозированием, прогнозированными значениями и, скажем так, выбирать в условиях ограничения времени тот или иной вид операции в первую очередь. Итак, гормональные показатели, как их восстанавливать? То, что мы имели, мы по биохимии восстанавливали. Я предложил добавить информацию дополнительную, используя цифровые стетоскопы и фонендоскопы. Там на протяжении 25 секунд идет сигнал. Я предложил, поскольку сигнал не стационарный, предложил вытаскивать параметры частотные и временные. Их 4 штуки. Для этого сделал дисперсионный анализ в окне наблюдения такого сигнала и доказал, что есть два комплекта по два параметра, два комплекта таких параметров, частотный и временной. Этим летом я провел эксперимент. Первое, начал эксперимент в Институте эндокринологии в Харьковском и параллельно в Институте, сейчас скажу, животных, кто работает.
Ветеринар.
Как же это? Ветеринарный, да. Там пчелы, ульи. И там звуковые сигналы пчел. Поскольку информация, звуки пчел уже были для разных биологических состояний, я проверил метод восстановления вот этого спектрального сначала на пчелах, а к сентябрю закончил испытания в Институте эндокринологии. Оказалось, можно восстанавливать состояние пчел, определять. И второе, можно восстанавливать дополнительно гормональные показатели. А теперь я перейду к математике. И уже буду и на французском, и на английском, и на русском.
Может перевести вот это?
Я буду...
Не, перевести может на английский вот эту вступительную часть.
Так. Так, если решишь...
Балфедович, может, Леша переведет на английский вступительную часть?
Давайте, хорошо. Но я посмотрю, по-французски.
We have enough time, so let's translate.
Je voudrais vous exprimer en français tout ce que veut. Premièrement, il y a le processus aléatoire, non stationnel. J'ai deux fenêtres. Et entre deux fenêtres, il y a le décollage. Je reconstruis le spectre en deux dimensions, en fréquence et en temps. Il y a 4 paramètres pour ce spectre. Et ces paramètres portent l'information qui nous utilisons, je peux décerner l'état biologique. Et c'est tout. Les paramètres hormonaux, par exemple, etc. C'est-à-dire, j'utilise les sons pour avoir l'information complémentaire. Et c'est tout. Bien, теперь на английском. Итак, давайте сначала по-русски. Итак, я имею нестационарный процесс. Он спектрально не стационарный. Это переходной процесс. За 20 секунд работы цифрового стетоскопа стационарность отсутствует. Я нахожу параметры изменения спектра. Это закономерности. Это не случайные параметры, они закономерные. Я что сделал? Я имею процесс. Да. Как сделать два окна наблюдения со сдвигом временным? Fenêtre de l'observation, c'est le processus aléatoire. Le deuxième fenêtre, c'est le premier, скажем, производная. Dérivative. И c'est tout. On aura le décalage. Oui. Итак, я имею процесс, а потом его дифференцирую. Я сдвигаю гармоники на полпериода в прошлое. В каждом окне я нахожу свой вейвлет спектр. Это трехмерный спектр. Вертикальная ось – это вейвлет гармоника, или как его, вейвлет коэффициент. Ось времени и ось частоты. ну, частота, там масштаб, обратная это операция, а ось времени это ось смещения. В каждом окне смещение это ширина окна. Дальше я нахожу корреляцию между составляющими спектра. Сейчас скажу. Je trouve la corrélation entre les deux paramètres de ce deux spectres, les spectres. Et j'ai 4 paramètres. Итак, j'ai le processus X et le premier dérivé est как это, I. I have the processus basic. Основной. The processus the first derivative. No, the first derivative правильно по-английски?
А что на русском?
Давайте по-русски.
Производство.
Давайте по-русски.
Первое
Давайте по-русски. Давайте по-русски. Все.
Давайте, хорошо. Потом, если надо, объясню либо по-английски, либо по-французски. Хорошо. Итак, я нашел корреляцию между гармониками, вейвлет спектра. Причем корреляция здесь, по сути, четырехмерная. Это первое. Корреляция между средними значениями гармоник и между шумами. Я анализирую не только первый момент, или начальный момент первого порядка, среднее, но и центральный момент второго порядка, дисперсию. Я нахожу, по сути дела, я делаю дисперсионное разложение вот коэффициента корреляции общего. Как разложить на дисперсию? Вспомните однофакторный, например, анализ дисперсионный. Мы имеем что? Мы имеем первую составляющую, лучше регрессия, простите, регрессия лучше подходит. Так, регрессия, линия и куча точек относительно линии. Находится дисперсия функции и дисперсия шума остаточного. Если дисперсия функции превышает дисперсию шума, все нормально. Регрессия хорошая. Если они одинаковы, это плохо. Есть F-статистика Фишера. Она позволяет найти качество этой регрессии. Здесь то же самое. Здесь разложение что? Сначала, вот я вам сейчас покажу. Да, вот я выделяю сумму, вот она. А дальше обычный дисперсионный анализ дисперсию. Получается две составляющих. Но одна идет по частоте, другая по времени. То есть я могу либо получить вариант первый, либо вариант второй. Вопрос, где больше информации? Я беру звук пчел, шум. Фактор влияющий – это наличие или отсутствие меда, или взятка, как там пчеловоды говорят. То есть мы, анализируя звук, определяем, пчелы голодные или пчелы сытые. Это чисто для примера. Второе, это, конечно, исследование в Институте эндокринологии, когда мне дают по 15 пациентам, измеряют гормональные показатели, это Т4 и альдостерон меряют. А дальше звук. Погрешность 15%, восстановление этих двух показателей. Теперь я знаю, что я смогу для раненых использовать дополнительно звуковой сигнал стетоскопа. Со своей темой, у меня есть своя тема, она уже заканчивается 2 года. Я хочу открыть другую тему еще, продолжение первой. Я хочу использовать дополнительную информацию по найденным гормональным показателям для прогнозирования операционных кодов, для сложных операций. Если я повышу точность хотя бы на 1-2%, это уже хорошо. Это поисковая работа. Она, кстати говоря, показывает, что можно это делать. В Молдавии такие исследования проводили ваши молдавские математики. Я нашел статью, вот, она у меня есть в перечне литературы. И там действительно они показали, что линейная регрессия позволяет дереконструировать les lacunes into databases. Английский. Пардон. Ну ладно. Короче говоря, взяли эти 4 параметра, ну вот они более расписаны, это уже в виде ковариации. Тут интересная вещь. Если я буду спектр находить, спектр для сигнала, у которого центрирование и нормирование провидно, то есть это случайный процесс с нулевым средним и единичной дисперсией, у меня автоматически слева будет стоять коэффициент просто корреляции. А справа ковариации, помноженные на какие-то там неизвестные коэффициенты. Но главное, сумма этих двух частей равна коэффициенту корреляции. Есть нормировка, короче говоря. Условия нормировки для коэффициента, нормированный коэффициент корреляции. Теперь, что было доказано? Сейчас я вам покажу. Да, это свойство. Ну, c'est sur les conclusions синтетик. Вуаля. Вот таблица. Значит, К1, К2, К3, К4. 4 параметра. Первый вариант и второй. Второй лучше. Если я использую одновременно 2 параметра, я повышаю вероятность расстояния махалономиса. C'est distance des махалономис. А что это означает? Это означает, что я могу рассчитать вероятность достоверного прогнозирования или диагностики, или распознавания. Это кибернетика пошла, по сути дела. Это обычный метод линейного дискриминантного анализа. Там используется так называемое расстояние махалономиса. Это расстояние между двумя классами, которые распознаются. Чем больше постоянное махалономиса, вот оно, тем лучше. Это постоянно дает доверительную, ну, дает la probabilité у него 0 нет. Короче говоря, 20 секунд сигнала, и мы уже что-то имеем. Чтобы повысить точность в 2 раза, надо в 4 раза увеличить время наблюдения. Значит, где-то 1,5 минуты хватает, чтобы достоверность была 0,95. Никто не мешает для пчел, к примеру, брать 30 минут, там сигналы очень длинные. Записывает смартфон, например. Короче говоря, эти результаты хочу использовать, чтобы открыть еще одну тему, как приложение той, которая уже есть. А эта тема, она первая, позволила спрогнозировать койко-дни при поступлении раненых. Я знаю, сколько он пролежит в госпитале. Второе, можно действительно спрогнозировать операционный код и подсказать хирургу, поддержка хирурга в решениях. Дело в том, что в военных условиях не все хирурги, может быть, и квалифицированы, действительно, очень много молодежи. А тут варианты. Я не просто прогнозирую коды, я даю 2 значения, а иногда 3. С разными вероятностями хирург может выбрать. Итак, вот такая работа. Что я могу сказать по поводу серьезности этой работы? Эта работа теоретическая, во-первых. Это должно быть глубокое статистическое обоснование. Здесь используются линейные регрессии. Если были большие выборки, можно было проверить бы на нелинейности. То есть это в перспективе. Но государство мне профинансировало вот эти 2 года. Я надеюсь, что получу финансирование еще на 2 года. Ну, не хочу, как это говорится, хвастаться, но первое. В прошлом году меня наградили крестом военным, да, за работу с военным госпиталем. Это раз. Второе, я получил президентскую стипендию в этом году. Я думаю, что это доверие государства, оно как бы обосновано. Вот и все.
Спасибо.
Это практическая работа. Мне нравится копаться с этой математикой, сидеть за письменным столом, кучей бумаги и писать. И действительно можно теоретически показать, что это можно сделать. Практика, эксперимент научный показывает. Ну, это все.
Все?
Да.
Вопросы, пожалуйста.
I wait for your question. En anglais, en français.
Скажите, пожалуйста, у меня вопрос есть. Можно? Во-первых, как вы перешли от нестационарных процесса к коэффициентам корреляции?
Сейчас скажу. Значит, что такое процесс, во-первых, стационарный и нестационарный? Стационарный – это случайный процесс. Единственное, что время не влияет на параметры. Здесь как раз параметры, я по сути нахожу переходной процесс, параметры переходного процесса за период там 15-20 секунд. Они есть. Какие они? Я не знаю функцию. Я взял функцию линейную. Да, информация есть. Если увеличить объем выбора, наверное, будет больше информации. Может, я перейду к нелинейной регрессии. Можно, да. Но главное вот что. Я нахожу корреляцию, связь между прошлым и будущим, смещенных на доли...
Меняется. Она же у вас меняется со временем.
Я беру только тот момент, когда там, вот же, сразу могу сказать. Есть переходной процесс, есть начало и конец. Он может даже не закончиться. Но вот 15 больных показали, что погрешность 15-20% восстановления – это уже небольшая погрешность. Да, это дальше будем думать. Что я могу сказать? Для меня, забыл сказать. Самое главное. Где j'ai fait la recherche de reconstruire les paramètres hormonaux utilisant les paramètres biochimiques. Ensuite, j'ai vérifié deux méthodes. Reconstruction, reconstruction des paramètres hormonaux et reconstruction utilisant la reconstruction des jours de réhabilitation. J'ai prognosé les paramètres de prognostic, le jour de réhabilitation utilisant biochimique et le paramètre hormonal. Le paramètre hormonal a été construit par les paramètres biochimiques. Le paramètre hormonal donne des résultats plus efficaces. Pourquoi? Parce qu'il y a la corrélation entre deux paramètres biochimiques. Я доказал сейчас. Как он по-английски показать?
Что?
Что? Ладно, да.
Павел Федорович, я прошу прощения.
Так, ладно.
Давайте в кулуарах.
Хорошо, договорились. Да. Короче говоря, вот такая вот... Короче говоря, восстановленный показатель гормональный работает лучше при прогнозировании койко-деятельности. Эти два показателя биохимических. Показали, что использовать для восстановления надо минимум два показателя. Один не работает. Да. Ладно, все. Вот давайте другие вопросы.
Так, нет вопросов, да? Все,
да.
Спасибо.
Да, thank you. Thank you.
Our next presentation, automated deep learning-based cell viability test for cells using phase contrast microscopic images.
Hello everyone. My name is Maxim Tafirians and I would like to present you our paper that we made together in cooperation between National Technical University, Kharkiv Polytechnic Institute and Institute for Problems of Biology in Kharkiv. So, let's first take a look at the problem we are trying to solve. There is a very common type of analysis that you do in biology called cell viability analysis. What happens during this procedure is that, let's say you grow a culture of certain cells, maybe a batch of these cultures, perhaps you apply certain treatment to them, and after a period of time you examine those cells to see how many of them are actually dead, how many are alive. So basically to see how the cells are doing. And what typically happens is that you have to take a lot of images, then you have to look manually at each image and count how many cells you have in total, and you need to see how many of them are dead. So this is quite time consuming, as you can imagine. So a human can spend around 30 minutes per 1,000 cells and produce quite a lot of errors. For example, for a human it's typical to make 3 to 10% error, miscount basically cells. Also, in this particular study we focused on a specific cell line called L929. This cell line is quite commonly used. It is derived from mouse connective tissues, and therefore we decided to focus on it. Also, we understood immediately that this is a very good area where we can automate this manual and tedious process. So here is an example of the data that we're working with. So on the left you see phase contrast images. They contain a fully grown cellular culture. It contains a huge number of cells. You can see there are hundreds of them. So imagine having to count all of these manually. Quite I can use this pointer. Yeah. Imagine having to count all of this manually. It can take a lot of time. Then on the right, this is an additional type of imaging that you need to make to perform cell viability analysis called fluorescence microscopy. So basically what you do, you inject a certain type of a dye into the cellular culture, and what happens is that it penetrates the membranes of dead cells and accumulates in those cells. And in this way, you can see how many of these cells are actually dead. And from these two images, you can say, okay, a certain percentage of cell has died during this culturing period. If you look at this problem, it's a twofold problem. So on phase contrast images, you need to count the total number of cells, and on fluorescence microscopy, you need to count the number of dead cells. And algorithmically speaking, fluorescence microscopy, counting images there, it's an easier task because what you have is mainly a black background, some noise, and clusters of these white active areas. So quite simple. On the other hand, counting these cells is quite difficult because there are many possible shapes, a lot of variation, a lot of ambiguity. Not even a human can tell for each particular case if it is 100% a cell or not, at least for many of these. Therefore, this gives us motivation to develop two separate algorithms, one for phase contrast images and one for fluorescence microscopy. Therefore, we proceeded in the following way. We developed two algorithms. For fluorescence microscopy images, we used a classical machine learning approach, and we were able to obtain the number of dead cells this way. And for phase contrast images, we were using a more modern deep learning approach, which provided us with the total number of cells. And from there, we were able to compute our target statistics, such as total number of viable cells, or ratio of dead to viable cells. These are valuable parameters for biologists. Now, let us focus on the classical algorithm first. Here is how we solved it. For this image, we first apply median thresholding. This converts the image from a grayscale image to a binary image where each pixel can have a value between only 0 and 1. From there, we can apply erode and dilate operations to remove the noise. Then we apply clustering algorithm that can actually give us information about each individual cluster that is present in the image. And then all we have to do is to remove anomalous clusters, and we have then our total number of non-viable cells. And here is an illustration of how the input is converted into the result using this algorithm. Here you can see that each cluster is highlighted in different color, and the red arrows pinpoint anomalous clusters that will automatically drop. These are most likely noise or some kind of an error. And here in this small table we have certain statistics. For example, here in total we have 1,200 active pixels. These pixels were clustered into 36 clusters, so you can assume 36 dead cells. But out of them, 12 will drop because they contained too few pixels. So 36 minus 12. Plus there were some points that were like complete noise, separate pixels, not connected to anything. And those were dropped too. Yeah. And here are the quality metrics from this approach. You can see that mean average percentage error and mean average error, they are quite low. So, for example, mean absolute error is just 1, meaning on average we have only one cell that is misdetected, that is not detected, or one extra cell that is detected. So quite nice working algorithm, but this is expected for this kind of data. Now, when it comes to detection of total number of cells, it is a bit more difficult, because here we need to work with a lot more data and use a deep learning approach. So for deep learning approach, data is crucial, and in our study we did not have too much practical data. We had just 100 images. Therefore, we had to source a public data set that is similar to ours, and then we split it into two standard splits: training split and validation split. From there, we were able to choose a convolutional neural network for our purposes, select hyperparameters, and start training and evaluation in order to obtain the optimal model. After this process of pre-training was complete, we were able to transfer the resulting model to use it on our data. And this model was able to give us the statistics that we wanted, specifically the total number of cells. And here is some information about the actual architecture of the model that we used. We used the YOLO V8 architecture provided by Ultralytics. This is one of them. Let's say it's one of the latest developments in the line of the YOLO family models that includes a lot of improvements, such as, for example, it has a hierarchical feature extraction, and it also has, let's say, certain features that allow it to detect objects of different sizes and shapes quite effectively. Here there is some information about the training setup. So, for example, we had around 3,600 images for training. These images were sized to 512 by 512 pixels. We trained the model for around 50 epochs, and the optimization goal was set as multitask learning, where we had three objectives that we were minimizing for. We had, first of all, optimization for box loss, meaning more precise bounding boxes around cells. We had class loss. This is training model to separate between the background and the actual cell. And distribution focal loss. This is like an additional extra that allows the model to focus on more on its weak areas where it performs worst. And also we used a stop condition to stop the training based on loss values before it gets worse, before the model performance worsens. And here is an illustration of the training process. We can see how these three losses behaved during the training and validation. So from the chart, it is clear that between epochs 40 and 50, we reached a point where validation losses, they became flat or maybe even started growing again. So this was the point where we decided it is the time to stop the training. And with this data, this is the best we could achieve. And here are the final results from this model. You can see that the trained model was able to detect cells quite nicely. It can detect almost everything in this picture. And it also is able to ignore the noises like these two objects. So it knows what is a cell and what is just some background noise or perhaps cellular debris, whatever. So this is a feature that classical computer vision models simply do not have. So this is quite useful. And here there are the quality metrics. We have precision and recall both higher than 0.9. And mean average percentage error, which is between 12 and 13%. So this is already, as you can see below, is comparable to a human. And one cool feature is that this model takes maybe around 30 milliseconds to make a prediction on the whole image. This is like 10,000 times faster than a human. So we can clearly say that this is a really useful thing. It can save tons of time for biologists, and it's only a first step. So there are ways to go to improve accuracy. Perhaps we can go down to like below 10% error rate, and that could possibly mean even getting on a level on par like with best human experts, or perhaps even better. So this was all presentation. Thank you for your attention, and please ask any questions if you have.
Your question, please.
Yes, thank you very much for a quite nice presentation. Fisher metrics here is absolutely fantastic, 92%. my question is, do you make any data engineering to these pictures? I mean, on cell count before to make this model training? Because then you rocks with these dead cells, yeah. You make this very typical for computer vision technology. You go to monochromic pictures, you make more contrast and so on. Here is, in my opinion, also could be a little bit improved. The very typical computer vision techniques to make more contrast pictures, for example, or something like that.
Yeah, could be. But the point of usually with deep learning, what you want to achieve, you want to work with original images, or at least images with minimum, let's say, modification, because deep learning model, it can fit whatever the data you show it. I mean, it can learn this augmentations by itself even. But I think we could try in our experiments to try to apply certain like contrast augmentation techniques and see if it affects the performance or not. Ideally, the model should learn it by itself, like because if the neural network is big enough and if the data is sufficient enough, these like augmentations can happen within the model itself, and because it's a trainable function. So yeah, but this is an ideal situation. However, we should definitely try it in order to see if it helps or not.
Okay, the next question here, if I correctly understand, you create the model, you train your neural network based on some public available data set.
Yeah.
Huh? That's the same data set for the same, this mouse tissue, no?
No, I have
some reference like that. Huh?
Yeah, so the data set is called live cell. It has, I think, around 7 or 9 different types of cells, but none of them are these mouse cells. They just resemble our data, but not 100%. And also the images, it seems that the microscope type is different. So it's the cellular cultures themselves, they're not as dense. You can see here they are quite dispersed. In our case, we have these dense, densely packed clusters. So this is one area, by the way, where we could improve, because we can collect more data from our biologists. Biologists label it and train on it and get better results for sure.
Somebody have to make the labeling for 1,000 images by calculating what is the cell and what is not.
Yeah, well, we have a plan here.
To use students.
There are students for sure, but students with additional neural networks, because there are huge neural networks trained specifically for automatically detecting what is cell, what is not, segmenting cells, called foundational models. For example, there are there is CellSAM, CellPose, huge like repositories where they develop specifically these huge models, expert models that can do this work. So we can, let's say, use students who use these models, segment cells, then maybe we can give this data to review for biologists. Not all, perhaps 10%, see what is the percentage like of mistakes, and from there we can already begin to see how accurate the data is. But I think the labeling can be obtained that is quite nice. But labeling such kind of data is quite tedious, as you can imagine, and it's costly. It's this live cell data set is only 4,000 images, which is considered quite huge for this area. But for like if you compare it with other data sets for computer vision, it's quite small, because what is 4,000 images? It's not much. Typically for computer vision, you want 10,000, 100,000 images, something like that.
For deep learning computer vision.
Yeah, for sure.
For traditional, we could use even quite smaller.
Yeah, but for deep learning, for sure, you want 100,000, 1 million, as much as you can, because all of this data will be absorbed into the model, and will be used to fit the function.
Max, I'm just thinking probably some geometrical informed things could be, constraints could be added here. I'm always appeal to this, to use something beyond the pure data, because that, in your speech you just say, okay, I need just as much pictures as could be, and then the model will train and will be okay.
Yeah, this is the approach. I mean, this is the approach used by like ChatGPT and the others. This is literally what they do: throw as much data as possible at a as big model of it as possible, and it seems to be like the best solution currently.
Probably not.
I mean, but Google engineers and Meta engineers think otherwise. So
Because they have a lot of money and time and students.
Yeah, yeah, for sure. But this is the industry standard.
Yeah. Okay.
Unfortunately, but this is how it works.
Another questions? Tell me please, and how are you going to improve the quality of your model if now it is nearly human quality?
Yeah, so as we said, we need first of all to collect more data that is ours and labeled by us and use it for training. So this will be number one priority. Number two, of course, is to look at more modern architectures and training pipelines, because basically every year, whatever model you used before, it gets outdated. So you need to constantly keep looking at the approaches. So these two things should be the priority. Also, how to improve beyond human, this is a question, because if you do not have what the standard here is, you need to somehow create at least labels that are more accurate than your average human. So here you would need to create a data set such that would allow to evaluate model first of all, because if the human labels the images, the error rate will be like in the image, its annotation itself.
So we should find a better human.
For sure. At least what we can do is to make one image can be labeled by not a single person, but by 5 different people. Then we compare the results, see if there are any mistakes between them, and like if we merge these 5 different results together, eliminate mistakes, we get a better outcome.
Thank you. Any more questions? Thank you.